your convective boundary condition would remain same at your as your temperature boundary condition. Only thing here you need from your convective boundaries, you have to get the expression of your this T naught actually, because you have to substitute previous one there. Your expression for T naught and expression for your last n one is Tn plus 1, right? Correct or not?
Yes, sir.
Yes, sir.
So that's what need to be done. And the derivation of this for bar case I gave. For this, I already have it here, so I would be able to show you. So discretize your boundary condition there. So if you will that discretize your boundary condition for left hand side one, you will get this actually. So this you are putting at I equal to 1 there. So from here, if you will rearrange it everything in properly, just the difference, this is just a formulation of the matrix first here. So you got T naught is getting in terms of T2 and all this. Then again you are so this is your expression by putting your equation again back in equation number 28 which we have previously. So this is now your next boundary condition in terms of convective boundary conditions here. Here it is wrong actually. This T2 should also move to this side because this is here actually. So only thing that need to be arranged in this particular format here. So finally you have this is the arranged one here. So this everything here is known to you. So this is now your new boundary actually. Fine.
Yes, sir.
Yes, sir.
Okay.
Yes,
So
sir.
once you have this, so same treatment you do for the last one. So last point here that I equal to n, discretize the boundary condition again. So you put here, then again you got the expression of Tn plus 1, substitute in the last equation previously for I equal to n, you will get this and rearrange it again. So you will get now this is your Tn minus 1 minus Tn again. And this is your last boundary condition here, boundary temperature, which is the expression of Tn plus 1 there. So you got this. So only these two changes you have to do, only first equation and last one. Rest of the matrix would remain same as you did of for the temperature boundary condition. So for this case, if you will do that, so this one, this is what, this is okay. So once you will get this one, so you will get these are the matrix actually. So matrix I wrote here C1 because if I will write everything here, this matrix would become so long and it won't be visible. So I just put here C1 here, C2 and expression of C1 is this one actually. So this need to be considered here. Expression of C2 is this one, which need to be considered here actually. Rest of the matrix is same. Correct?
Yes,
Yes,
sir.
sir.
Does it look interesting or boring?
Interesting, sir.
Interesting. For me, it looks interesting because we have put attention just to write one program, right? If you have wrote at least one program your own, after that it's just a extension and we are solving it from just a bars to cylinder to sphere with some modification only, just a modification, right?
Yes, sir.
Yes.
So in that way it seems to be interesting. If you have wrote at least one program well, rest can be changed without much complication actually. Then this is now your boundary condition matrix. So boundary conditions only change in first term here. So you got this term extra, right? This one only. The rest term was there. Same thing here, this term. So once you have all the matrix, take the inverse and all this and solve it. And these are the commands just to give your the generation of the matrix there. So if you so this is what you need to be think before you write a program actually, that this is what need to be done on paper first. So you wrote once, so for that is fine. So you think that how this could be generated. So this is your boundary condition, first element. This is your main diagonal one. Then for I equal to 1 only, you have deliberately wrote I equal to 1. So this is your the second element of the first row, which was I mentioned there, the C1 actually. So this is there. After that, in between from I equal to 2 to I equal to n minus 1. So these are the your left diagonal. This is your right diagonal one. I equal to n, last one. You wrote this one. This is your the second last element, and this is your boundary only. Boundary condition, last element only. Once you have generated that, after that I wrote the program for this. So before program you have is analytical solution because it's slightly bigger as compared to the cylinder and everything. So therefore I thought less to share with you because you may try. So if you have there, so this is what you have. You want to integrate it, so you have integrated. Finally, you got this expression, right? Correct.
Yes, sir.
Now you have
Yes, sir.
easily two boundary conditions. So for that case, first boundary condition, you have flux at R naught. You are putting this. So you know from the previous one what is your expression of dt upon dr. So dt upon dr, you have this one, right? C1 upon R square. Correct.
Yes, sir.
So that's
Yes,
what
sir.
you have substituted here. You got here C1 upon R square. So you are calculating at R naught. So you have just put R naught here. So you got this. A same thing at R equal to Rn plus 1. So here you have just put Rn plus 1 here. So you have two equations now, right? So one equation, this is also in terms of C1. This is also in terms of C1, right? Now you have this, so you can write equation for your T naught and Tn plus 1, and somehow you have to solve equation number this one and finally this one. So this practically same, I hope, in previous one also. Not that much same. So if you can obtain by subtracting, so that's what you will subtract your equation 10 and 9. So you will get this and then divide equation 3 by this, you are getting something like that. And then you have to subtract above two equations, you will get this equation again, C1. So from practically from here, you are getting the expression of C1 first. Okay.
Yes,
Yes,
sir.
sir.
Yes,
So
sir.
from here you got rearrange it everything. You got the expression, final expression of your C1. Now to get the expression of C2, I did this one, equation 9 and 10, add it up, and I ended with this one. And then again the subtract equation 12 and 13. So I got this one there. So this I will substitute here, and this expression I already know from here. T0 plus Tn plus 1, this whole thing would come here. Right? You have here also this Tn plus 1. Here also you have this. Substitute this
Yes, sir.
entire term here. You know the expression of C1. So only unknown here is C2 only. So that you will get the expression of C2 from here. So finally, you will rearrange this whole thing actually. So you would get your C2 expression in this actually practically. So everything here, if you will find, everything is known. There are no terms here T naught or T1 or T2 or something or Tn plus 1. Everything in terms of TG1, TG2 and all HG1 and HG2 only, right? So you will get this one, and finally, if you this is your expression of t is minus c1 upon r plus c2. So you have an expression of c1, c2, and this is your final expression of your temperature in terms of convective here, boundary conditions. So this is your final expression of temperature. Only variable here is r only. This one is r. Okay.
Yes,
So
sir.
you give your full try and you will get it. So no problem for that. So once you have this, you can calculate your heat transfer rate minus k dt upon dr. So you will calculate this, and finally your this is your expression of your heat transfer rate. So you see here R is not at all there, right? It's just independent of that.
Yes, sir.
So you have this. So in case of steady state, it happens that way only. So you are getting this is your heat transfer rate. Temperature you got previously. Now you can write your MATLAB code actually. So by putting all those conditions. So if you will write the MATLAB code, so you have this R2 minus R1 thing. After that, you are generating your matrix first A matrix. So this is your R you are calculating. This is your Venn diagonal term here, right? This is your Venn diagonal immediately you are putting a condition one here you are calculating. This is your second element here. Okay, A12. This is there. Then from I equal to 2 to n minus 1, you are putting your left diagonal. This is your right diagonal one. After that, you went to the last row. So last row, you are this is the expression. Just you are calculating only second last element of your last row because main diagonal is being calculated. So this is your second diagonal one. Once you have this, now you have boundary condition matrix. So you have first boundary condition that this you have the expression for that. Second, the last boundary condition, this is this one only. In between you have zeros only. So zeros would automatically filled by MATLAB. Once you have A matrix, once you have B matrix, you got your temperature at the difference point by this. In this, you want to add the temperature of the boundaries. So you have boundary temperature, first one here, second one here, in between body, you are getting temperature calculated from here only. Okay, so you have now complete your all calculated temperature from boundary to end. Radius you have from here. Once you have this, you can plot it with radius versus the temperature there. This is just a command just to have font size, radius, fonts, and font weight. After that, you want to calculate heat transfer rate at all the difference points. That how did it change actually, and you are calculating this from here. After that, you want to compare all solutions with the analytical one. So you know the analytical temperature expression you can use here. Then based on that, you are calculating percentage error. So once you have this, and then you are calculating analytical heat transfer rate also, and also the error in the heat transfer rate. These are again the same plot command which we use this. We want to plot it error and temperature in one graph, and same thing for your absolute error part also, right? So you can plot everything in one graph. These are again same command just to give their decoration part, line, weight, color, and everything. So the example for this, the data actually. So data for this again, you have taken R equal to 80 centimeter and outside R is the 90 centimeter. Thermal conductivity of the material is given to 45. And here convective heat transfer coefficient is taken is 9 inside one and outside one is taken as 25. Air, because they typically have air heat transfer coefficient is 25 degrees Celsius is 24 watt actually. Watt per meter square per degree Celsius. Analytical temperature, we already did the derivation of that, so you should also do that actually. So you will get this one. Analytical heat transfer rate would be given by this, because you got previously expression is minus 4 pi k C1. So this was your expression of C1, right? Hello?
Yes, sir.
Yes, sir.
So once you have generated everything, and after that you will get this graph there. So this is your temperature graph. This is your absolute error one. So once you have did the calculated that, so this is what you have in case of your convective boundary conditions. Okay.
Yes, sir.
Do you want to have a break of 5 minutes before I can start your partial differential equations?